Hello everyone, today I'm going to introduce our work, Unbiased Scene Graph Generation from Bias Training. The proposed method can be concluded into 3 steps, but before diving into the details, I will talk about our motivation and some prerequisites. This paper aims to tackle the existing long-tail distribution problem of scene graph generation. It is also commonly observed in most of the real-world data. The problem is, in not just making the existing methods to be highly biased, it also causes the model to predict only trivial relationships, simply because of their higher frequency. For example, trivial predicts on or near, dominating the output scene graph. You can imagine a detector detecting everything as an object. A dog is an object, a cat is an object, and the bicycle is also an object, which makes this whole task meaningless. While the proposed unbiased scene graph can successfully infer much more fine-grained predicates. To get started, I will introduce the concept of causal graph first. To understand why we need a causal graph, we should point out a common misunderstanding in data science. The input data is not the more the better. The problematic inputs can cause a prediction taking the false shortcut. Here is an example. To predict the crime rate, if we take all the related inputs, the ice cream sales and the temperature, the model could take the shortcut from S to C, which doesn't make sense. Why is it happening? Because in the summer, the temperature will increase, which causes ice cream sales and the crime rate increase as well. With the help of causal graph, we know how to design the correct model and how to cut or separate the biased shortcut. Then I want to introduce the proposed unbiased inference into just 3 steps. The first step is the roadmap. We reconstruct a causal graph of the network to understand how it predicts the scene graph from an image. This causal graph has been adopted by most of the recent approach in scene graph generation. Although all edges in this causal graph are valid, they are not equal, so the shortcut can still occur and hurt the unbiasedness. That's why we need the next step. We use counterfactual thinking to identify the source of the bias. I visualize all 3 input variables for relationship prediction. They are object features, object labels, and background environment features. The conventional inference considers the entire model as a whole and only gives a one-time likelihood. But if we consider the model as a causal graph, the prediction can be intervened to perform the counterfactual thinking. For example, in scene graph generation, we found that even if we set the object features as dummy vectors, the prediction is still almost the same as the origin, which means the bottom right counterfactual case creates a shortcut. This is a pure blind guessing that we definitely want to avoid. So here comes the solution. Our final step applies the total direct effect that removes the above-mentioned bad bias and gets the unbiased part of the logics, which corresponds to the visual part but still under the same context. Note that our training phase is still conventional biased training, so we only need to run the inference model twice. The result is quite amazing. Given the same trained neural motif model, after applying our unbiased inference, we almost perfectly remove the long-tail distribution appeared in the performance. The tail categories can perform as better as the head ones. The only thing hinders the performance is the difficulty of each categories, but not the distribution anymore. There are 3 advantages of the proposed unbiased inference. It's model agnostic, simple, and effective. We compare 3 base models, neural motifs, VTranC, VC-tree, and 2 fusion functions, sum and gate. The TDE significantly improves the original likelihood prediction in all cases. We also compare conventional debias method, reweight, resample, and focal loss. Note that although reweight seems better than TDE in scene graph detection, but if we look at zero-shot recall, reweight got zero recall in the same scene graph detection, which means the unbiasedness of reweight is not generalized to new cases. We also test the scene graph-based retrieval. The improvement in retrieval means the TDE-based scene graph contains more discriminative information, so it can be easily retrieved. Here are the qualitative examples. The yellow box means conventional inference, and the green box means TDE-based unbiased inference. The interesting part is, for the button image, the conventional inference is totally blind. It considers that the girl is holding the kite even she didn't touch it, while the TDE-based inference correctly predicts the looking-at relationship. Thank you for your patience. If you are interested in our work, please scan the QR code of our project and the paper links.